Hi, this is our project Abnormality Detection and Prediction on Unseen Diseases in Chest X-ray Images. The motivation for this study comes from the challenges faced during the early COVID-19 pandemic in diagnosing COVID-19 in patients based on X-ray images. In the beginning of the pandemic, there existed no labeled COVID-19 data to train any deep learning models on. In this project, we used computer vision and deep learning to detect abnormalities in chest X-ray images and later applied the model on patients with diseases that the model was not trained on. The first dataset we use is the NIH chest X-ray dataset. It has about 100K labeled chest X-ray images with a total of 14 different disease labels. COVID-19 is not included in this dataset. We use the dataset for model training and validation. The second dataset is a COVID-X CXR2 dataset. It contains about 30K chest X-ray images with a binary label of whether the patient has COVID-19 or not. We use this dataset to test our models on an unseen disease. Here's a disease distribution of the first dataset, and here's the correlation between different diseases. The first task is to find the best deep learning model architecture for binary abnormality detection. In the second task, we use the best model architecture from task 1 and exclude one of the 14 diseases during training. We evaluate how well the model performs on the held out disease. We also evaluate how well our model performs on the COVID-19 dataset.
We use transfer learning and a caveat strategy to pick the models for our case study. The caveat strategy means we develop and train multiple models and select the model which has the best learning curve. Our strategy is to filter the models available from the Torch Vision package, pick some of the best models with the highest top 1 accuracy on ImageNet, as well as having the ability to train efficiently without CUDA running out of memory, and then conduct transfer learning on the chosen pre-trained models. So following this strategy, we have picked the following 8 supervised learning models. We use binary cross entropy loss and add an optimizer for 10 epochs. Moreover, each model is followed by one or multiple following connected layers, along with ReLU activation function, a dropout layer of 0.2 to prevent overfitting, as well as a sigmoid layer at the end. For the evaluation metrics, we decide to evaluate our models using the following metrics, which include precision and recall, F1 score, Matthews correlation coefficient, and also for sure the ROG AUC score.
Here are the results of training the 8 models for task 1. You can see that VGG19 and MNATNES 0.5 suffer overfitting heavily. We also evaluate our models using our evaluation metrics. Looking at table 3, we can see that Inception V3 has the best precision and MCC score, while DensNet 121 has the best recall and F1 score. Here are the ROG curve and AUC of our 8 models. VGG19 and MNATNES 0.5 has the lowest AUC score as they overfitted. And based on this plot and the evaluation metric table, we decided to keep Inception V3 and DensNet 121 for test 2. For test 2, we use our previously chosen models DensNet 121 and Inception V3 to see whether they can predict an unseen disease. Based on table 4, overall, Inception V3 had better performance on locally held out disease such as infiltration, consolidation, or hernia of the chest X-ray 14 dataset. But when we tested on the completely separate dataset of COVID-19, DensNet had a slightly better performance. It's also worth noting that our recall score of our 2 models for COVID-19 are above 0.9, meaning that they are able to identify more than 90% of images that has abnormality of COVID-19. This is very helpful for our medical fields as our models are able to identify defective samples of an unseen disease with very high accuracy.
Discussion. In task 1, we conduct a case study to compare a supervised learning model on detecting abnormalities caused by one or more disease with high accuracy. In task 2, we simulate few-shot learning by hair or some disease, and model can still manage to correctly predict those diseases as newly emerged. With relatively high accuracy, we are able to detect abnormalities in COVID-19 patients without having COVID-19 data in the training data. Limitation. In the real hospital setting, we still need to train medical personnel to consider other symptoms that are not measurable by X-ray image before finalize the diagnosis. For task 2, we ideally want to test our 8 model from task 1. However, given the limited computing resource, we choose to test only the best 2, namely DesNet and interception, using task 1 as the benchmark. Future work, we can extend from binary classification to multiple class classification, so that we can not only predict whether it's unseen or not, but can also classify known disease. We can create a silency map to show an area that contribute to the diagnosis of the given class. Moreover, we can compare the general purpose classification model, such as VetNet and EfficientNet, which have been used in these talks, with the task-specific models such as EggNet in few-shot learning setting. In conclusion, in this paper, we have shown empirical results that it is possible to use transfer learning to help classify newly emerged pandemic from shared data without seeing the data first. We hope this success of the model will help lower the barrier of applying deep learning to assist diagnosis at the start of the pandemic and consequently facilitate medical staff to help patients more efficiently.